We can better understand precipitation reactions by looking at the reaction quotient. Remember that guy a couple chapters ago? The reaction quotient is calculated the same way as the equilibrium constant. But at K, the equilibrium constant is calculated where it is at equilibrium only. Q, you can calculate that under any set of conditions. It can be unsaturated, saturated, or even supersaturated. And we can compare Q to the KSP, and then we can predict, well, is more going to dissolve? Is it already saturated? Or are we going to expect things to precipitate out of the water? So if Q is less than KSP, if this is smaller than KSP, that means that these numbers are also smaller, right? And so we can increase these until it matches KSP. At equilibrium, Q is equal to KSP. If you add more solid, it's not going to dissolve. When Q is greater than KSP, we have concentrations here that are higher than at equilibrium. That is not a stable situation, and most of the time, it will precipitate out. The reaction will proceed to the left, forming solid precipitate until these reach the equilibrium values. So we can use Q to predict whether a precipitation will occur when two solutions are mixed. We first have to identify what's the possible precipitate, and then we're going to calculate Q for that potential precipitate. If Q is larger than KSP, we can expect precipitation. Let's do an example. A solution containing lead-2 nitrate is mixed with one containing sodium bromide to form a solution that is 0.06 molar in lead nitrate and 0.0158 molar in sodium bromide. Why does my brain do that? Does a precipitate form when you mix these two solutions together? So they're being kind to us here. They're not giving us concentrations of each of the individual solutions and then making us calculate what it is when you mix them together and the volume changes and all of that. So we could be thankful for that. Okay, so we are given KSP for PbR2. If you remember solubility rules, sodium, in fact, all the alkali metals, sodium, lithium, potassium, plus ammonium, they don't form solids with anything. And nitrate is one of the anions that just doesn't precipitate, nitrate and acetate. So we have to predict what the product is, and we've got a big hint because they gave us KSP. So the possible product then is PbR2. PbBr2. I lost a B in there. So we'll write the equation for that dissolving. And what we want to do here is we want to calculate Q. We are given initial concentrations. So the lead is 0.0600 molar, and the bromide is 0.0158 molar. We're not calculating equilibrium concentrations. We could do that, but all we need to do is calculate Q and compare it to K. So Q, it's the same equation as for K. But it's not at equilibrium necessarily. So Q is going to equal these initial concentrations. 0.0600 and 158 squared. So that's the value I get for Q. I'm not going to multiply this by 2. This is just the concentration. I need the concentration of Br squared. So then we're going to compare that to KSP. KSP is 4.67 times 10 to the minus 6. So the whole greater than, less than thing is hard to remember. So I just prefer to think about it. So this is where we are right now, and this is what it's going to end up at. How is this going to become that? Are these numbers going to get bigger or smaller? These have to get smaller for this to get smaller. How do these get smaller? By precipitating. So this is greater. Does it precipitate form? Yes. Any questions?
Would
Yeah.
it be given to us in the prompts and stuff telling us that it is soluble, or do we have to remember the whole solubility chart again?
Well, we don't really care about the solubility rules anymore because we're going to be using KSP, which is kind of a good news, bad news thing. So we're not going to say, oh, this is soluble or that's not soluble. We're going to say, well, which is more soluble or which is going to precipitate. Because now we understand that those rules are a guideline, but it's a continuum, right? Just like if you try to talk about, family income and you say, well, these people are wealthy and these people are middle class and these people are poor, soluble, somewhat soluble, insoluble. Well, where's the dividing line? There's no hard dividing line because there's a continuum. Good question. Anybody else? Selective precipitation. So we can use precipitation to our advantage to separate different ions. So selective precipitation is the process in which you add a reagent that forms a precipitate with one of the dissolved cations in a solution, but not with the others. So you can precipitate one out and leave the others, and this allows us to separate ions. So you choose the reagent based on KSP values for the possible compounds. We want to have a difference in KSP values that's a factor of at least 1,000. If the KSP values are really close, you can only get a partial separation. The concentration needed to trigger precipitation is determined by comparing Q and KSP, like we just did. So a solution contains equal concentrations of barium, lead-2, and calcium ions. When potassium sulfate is added to this solution, which cation precipitates first? So what are the possible precipitates? We could get barium sulfate. We could get lead-2 sulfate. Or we could get calcium sulfate. If you add enough sulfate, they're all going to precipitate. But as you slowly increase the concentration of sulfate, one of these will start to precipitate before the others. How do we predict which one? Will it be the one that's the most soluble or the least soluble? The least soluble, right? The least soluble precipitates first as we're adding sulfate. Well, how do we know which one's least soluble? Hint, see table 18.2. Oh, conveniently there is table 18.2. I got tired of jumping around. Okay, so here's barium sulfate. Let's highlight these guys. There's barium sulfate, that's one of the possibilities. And calcium sulfate. And lead 2 sulfate. We're just going to look at their KSP values. We're looking for the least soluble. Will that be the smallest KSP or the biggest KSP? The smallest. So we're looking for the smallest. We've got 10 to the minus 10, 10 to the minus 5, 10 to the minus 8. I think barium sulfate is our winner. Barium sulfate will precipitate first. So you have a solution of these three cations. As you add potassium sulfate, you'll start to see, at some point, you'll start to see a precipitate form. That's going to be barium sulfate. Any questions? So this is a good exam question. The magnesium and calcium ions present in a solution can be separated by selective precipitation with potassium hydroxide. What minimum hydroxide concentration triggers the precipitation of the magnesium ion? And we are given KSP for both of these. So these have the same stoichiometry, 1 cation to 2 anions. And so when we look at these, this is the smaller KSP, and so we understand that's going to precipitate first, right, which agrees with what this says. Anytime you're not sure what to do for problems like this, it's always a good idea to start by writing a chemical equation so you can look at what's happening. So magnesium hydroxide forms these ions. We could calculate the concentration of magnesium in a saturated solution, but there's no point in doing that. We are told what the magnesium concentration is. It's 0.025. So this is 0.025 molar, and we want to know what concentration of hydroxide do we need to begin precipitating. This is finding the hydroxide ion concentration at equilibrium, because adding hydroxide, as soon as this gets to equilibrium and you add more hydroxide, that's when the precipitation starts. So by triggering precipitation, we mean this is where it's just going to start precipitating. So this is what we want to know. We'll just call that hydroxide concentration. Well, KSP is equal to magnesium concentration times the hydroxide ion concentration squared. KSP is given to us, 2.06 times 10 to the minus 13. That's going to equal the magnesium ion concentration. times the hydroxide ion concentration squared. And this is what we're trying to find. So solve that using your preferred method. So this is the minimum hydroxide concentration that's going to start the precipitation. That's going to make it saturated. Tiny smidge above that, it'll start precipitating. Any questions? This is another kind of question. Finding the concentrations of ions left in solution after selective precipitation. So here we have a solution with lead 2 ion and silver ion. And it's asking us two different questions. A, if selective precipitation is to be achieved using sodium chloride, what minimum concentration of sodium chloride do you need to begin to precipitate the ion that precipitates first? And then it asks, what's the concentration of each ion left in solution at the point where the second ion begins to precipitate? Well, let's not think about B. Let's just think about A for now. So which of these will precipitate first? The stoichiometry here is not the same, right? This is 1 to 2, and this is 1 to 1. But these KSPs are not even close, right? This is 10 to the minus 10, and that's 10 to the minus 5. So, pretty good guess that this smaller one is the one that precipitates first. If they were closer, then you'd have to look at it with the stoichiometry. So I'm going to assume that it's the silver chloride that's going to go first. And if we do the problem and we were wrong, we'll find out. So that's the equilibrium for silver chloride. And we are told that we have a concentration of silver that's 0.025 molar. And it wants to know what the chloride ion concentration needs to be for that to precipitate. So this is like the problem we just did. KSP equals silver ion times chloride ion. The KSP is given to us, 1.77 times 10 to the minus 10. That equals the silver concentration times the chloride concentration. Oof. This one is so small, I'm going to switch my calculator into scientific notation mode. 7.08 times 10 to the minus 9 molar. So when we get to chloride ion concentration of 7 times 10 to the minus 9 molar, the silver will begin to precipitate. That's the answer to the first question. The second question is, what's the concentration of each ion left in solution at the point where the second ion begins to precipitate? Well, at what point does the second ion begin to precipitate? We need to do the same problem for the PbCl2. We are given the concentration of lead is 0.085. And so we know that KSP is equal to the lead concentration times the chloride ion concentration squared. Pay attention to those coefficients. The KSP is 1.17 times 10 to the minus 5, and that will equal the lead concentration times the chloride ion concentration squared. So we can solve for the chloride ion concentration. I'm getting 0.01173. Anybody else get that number? Yeah. So as we're adding sodium chloride, when the concentration gets to 7 times 10 to the minus 9 molar, the silver starts to precipitate. As we add more and more, the silver just keeps precipitating. The lead is not going to precipitate yet. The lead won't precipitate until we get up to a concentration of 0.01173 in the chloride. So they are asking us, what's the concentration of each ion left in solution at this point? Well, the lead ion at that point has not been affected yet, right? And the chloride ion concentration at that point is this number. The one that we have to calculate is the silver. So we're going to go back and look at our silver calculation. Now we have a chloride ion concentration of, oops, that's not what I meant to do, 0.01173. That's our new chloride ion concentration. And we want to find out what is the silver ion concentration. It's going to be less than this because a bunch of it precipitated. We're going to use our KSP again. 1.77 times 10 to the minus 10 is equal to, this time we're looking for the silver ion concentration when the chloride is 0.01173. And I'm getting 1.509 times 10 to the minus 8. .5 times 10 to the minus 8 molar. And it says each ion, right? So the other answers, the lead, the concentration this is just about to precipitate, and so the concentration is the same as it started out. The chloride ion concentration is what we calculated here and what we used in this second calculation. 0.01173 molar. There's three ions, there should be three answers. Any questions? So, are we completely separating the lead and the silver? No. If we stop here, our solid should be pure silver chloride, and we could filter that out. But we're still going to have some silver ions left in this solution. So we've separated them, but there's still one of the pieces is a little bit mixed. But this is a very small concentration. Any questions? Here we go. Oh, I forgot about the sodium. And that answer was a little screwy because it's not sodium chloride, is that concentration? It meant sodium. So how do I figure out the sodium? Well, sodiums came in with the chlorines, right? So I have as many chloride ions as sodium ions in there. And how much of the silver has precipitated? Well, this is the new concentration, right? And that was the original concentration. So, 0.025 minus 1.5 times 10 minus 8. It's really not any different. This is where things can get a little circular. Because if you think about this, okay, so as I'm adding chloride ions, this is the concentration I currently have, but is that how much I've added? No. I've added a little bit more because I've precipitated some of the silver. And so that's not showing up here. This is what's left after the silver precipitates. So what's the sodium concentration? Well, the sodium concentration is what came in with the chloride plus the chlorides that got used up. In this case, we would take this number and add this number, and this number is so small that it's going to be the same. Oh, I know what that answer was. This is the answer to the first question. And these are the answers to the second question, and they're not caring about the sodium chloride, so that was for nothing.